Hi everyone, again. Uh, Today we're going to be dealing with quantum circuits. And the the index of today's lecture is going to be this one. At first, I'm going to discuss a little about the evolution of quantum systems. After that, I will explain what are classical gates, and after that, we will go to quantum gates, then explaining what is a quantum circuit. And after that, we will also see control gates. That is a special type of gate, sure. Finally, we will discuss a more or less easy example of a quantum algorithm in order to see how things can work. So let's go ahead. So evolution of a quantum system, and this is important because at the end, when you are doing some computations, there is an evolution over time, right? I mean, you start at some point in the calculation, you have to do some physical things to your qubits, right? Because remember that in quantum computing, we are working with qubits. That's our physical system. So at the end, quantum circuits are going just are just going to be some kind of operation that evolves your qubits over time. So that's why it's important to understand a little of quantum the evolution of a quantum system. So without needing to understand the details a lot, right? But I always want to explain things properly. But I know this is quite more difficult. So here we have the Schrodinger equation, right? It's this equation over here. And we have this partial derivative over time, and this is the Hamiltonian. And I believe I haven't said anything about Hamiltonians until this point, so I added this explanatory uh, square. So basically, a Hamiltonian, the Hamiltonian of your physical system is a linear operator. Well, yeah, basically it's a linear operator that represents the energy of the system. So depending on the system, the Hamiltonian can be different for sure. Has all the information relating to the energy. So and that's basically a Schrodinger equation. Yeah, you have here your bracket, and we yes with this x and t here. The only thing I mean that this vector, this ket in our Hilbert space can depend on the position, right? The position is labeled as x in this case, and also the time is the only purpose of writing this here, because since this is a differential equation, this means that you are trying to solve a function, because I guess that you are not familiar with the differential equation since you're a high school student. So this is a partial derivative. This is the Hamiltonian of the system, and this is just our vector. But our vector is a function of certain variables such as the time or the position, right? So you can solve this equation in, for the because this is not complicated if you have some knowledge in solving differential equation for sure. But since we don't have that knowledge, and I'm not going to be explaining that, so this is just a part of the solution that you can do in general for every Hamiltonian. If the Hamiltonian does not depend on me, if the Hamiltonian does not depend on time, I mean, because the Hamiltonian could depend on time, but for most of the, let's say, non-extremely complicated cases, the Hamiltonian does not depend on time explicitly, right? I mean, there is not explicit the dependency of time in the Hamiltonian. But these are just details, because I know that you are not probably understanding why we need that or anything. But the point is that at the end, you can solve for this operator, right? And this operator here is called the time evolution operator. So at the end, you have an initial time zero, and your final time, the evolution between for the state in the initial state to get to the final time is given by this operator. Mm, right? So if we have here the state at the final time, and here the step at the initial times, the relationship between these two states is the evolution operator, and it's given by this equation. And this is taken out of the Schrodinger equation, right? So one funny detail here is that we have an exponential, right? And this uh, Hamiltonian is a linear operator. I mean, a linear operator can be described by a matrix, for example, or when things get more complicated, for example, infinite dimension, they cannot even be written as a matrix because they have infinite uh, elements, right? You have infinite elements in your basis, so you cannot write it as a matrix. So the point is, what's exactly the meaning of this? In the sense that is a exponential of a linear operator that can be, for example, a matrix. So every time you face some expression like this, I mean, some strange factor, for example, you can also see the square root, the square root of the Hamiltonian, for example. I mean, it's not usual, but you could, or any other linear operator, or maybe the logarithm, right, or a linear operator, or something like that. I mean, when you see a function that we are used to apply to numbers, right, but not to matrices, with matrices, I mean linear operators. In this case, it's not general, but in this case, we are going to be dealing with that. So that's why I say that. So what you really mean is that you are referring to the Taylor series of the corresponding um, function. Yeah, I mean, remember, for example, that the exponential of x would be written as a sum over 0. I think it was 0. Uh, mm, mm, pero, yeah. Yeah, I guess it was this one. If I'm not remembering badly, this should be the sum. So remember that we could write the exponential in this way. Need to search for it. Uh, uh, so if we write um, our, oh my God, mm, yeah, our exponential in this way. Anyway, if we write our exponential in this way, we will just take. I mean, if you have here an operator, I mean, I'm not going to the other things. I just number. I mean, this is the imaginary unit. This is the well. I don't know if you know this number. This is a physical constant called h bar, right? It also appear here. The h bar. This is the imaginary unit. Uh, So these are just numbers and this is time. So I mean, this is just a linear operator multiplied by certain numbers and the imaginary unit and that stuff. So you have here a linear operator by a number. You just have to change this, right? And this is the real operator that you are referring to. You are referring to this sum over here. Uh, I guess that's. I hope that does make it a little more clear like this expression in the exponential. Anyway, these are all, I would say, details because this is not this exactly this point on solving a differential equation and everything is not really a key to understanding quantum circuits. But the importance in here is that this operator is given by a Hamiltonian. I mean, it depends on your physical system and gives you the time evolution of a quantum system. So what's the funny thing here? The Hamiltonian is a self-adjoint operator for sure, because remember that any physical quantity in quantum mechanics or quantum physics is represented by a self-adjoint operator. So since the the Hamiltonian is self-adjoint, it means that the unitary operator, sorry, the time evolution operator, and that is this guy here. If you do this operation, if you calculate the adjoint of the time evolution operator and multiply it by the time evolution operator, you get these exponentials. At the end, this is equal to the identity for every Hamiltonian, right? I mean, since the Hamiltonian is self-adjoint, it doesn't matter what kind of Hamiltonian it is. So I mean, it satisfies this identity. So when any operator, any linear operator satisfies this property, and this is just what we have seen here, right? It is called a unitary operator. And unitary operator are great. I mean, to have unitary operator is quite great because it preserves the scalar product in the sense that if you apply this to random vectors of your Hilbert space, and remember that I mean this is just the adjoint of, right. Remember that this is just the adjoint of this one. So you are just applying your operator to the bra and the ket using the corresponding adjoint operation. Is we have this property. At the end, the scalar product between these two vectors is going to be the same as the original vector. And that's a very important property because it wouldn't make much sense if you have some, for example, orthogonal vectors in the at the beginning of your time evolution, right? And you apply the evolution, and after a certain time, these vectors are not orthogonal anymore. So that wouldn't really make much sense. So preserving the scalar product is a important property, and it comes from the unitary evolution of the quantum system. So this at the end, the important idea that I wanted to talk about is that the evolution of a quantum system is given by a unitary operator. I mean, this is an unitary evolution of time. And this is going to be important for quantum circuits. So let's now move a little into classical gates. This is just for you to maybe understand a little how computations are going to be working in the bit and qubit level. So a gate is just a logic operation performed in binary input, and you produce a binary output. That's basically it. For example, we have a very typical gates here, just as an example. For example, see the NOT gate. The NOT gate can have an input of 0 or 1, and it's just basically if you have 0, it gives you 1, and if the input is 1, it will give 0, right? That's the called the NOT gate. It takes 0 or 1, and it gives you 0 or 1 depending on, yeah, in this case, it's just 0 gives 1 and 1 gives 0. So, for example, the AND gate is a little more complicated, not that much anyway. The AND gate is just you need to have is you get two inputs in this case, A and B, and in order to this to be one, A and B, but both of them needs to be one. It's like I don't know if you have you know something about Boolean computing stuff, but this just means that in order to be true, you have A and B. If you want this to be true, you need A equal B equal true, because you need this and this, right? You need both things in order to be true. So, but if you don't know anything about Boolean systems, it might be seeing a weird explanation. So doesn't matter that much. Only know that this gate, you have 0 and 0, you get 0, 0 and 1, 0 and 1, you get 0, 1 and 0, again, you get 0. And if you have 1 and 1, right, 1 and 1, you get 1. That's the AND gate, right? It takes two qubits, sorry, two bits, classical bits. We are talking about classical gates right now. You take 2 bits, and the output is just 1 bit, following this rule, right? Also, the OR gate, uh, this is just A or B. I mean, in order to be true, you only need to be A true or maybe B, right? I mean, I guess it's quite self-explanatory. So they can be both true, and that will still work. But if this is the only one true variable, this will still be true. So basically, at the end, if you have 0 and 0, it will be 0. But for the other combination, you always get 1, right? So these tables, I have taken them from Wikipedia. You can find there more information about this in case you are interested. But let's move into quantum gates. So quantum gates, the idea is the same. You have, instead of bits, you're going to have qubits for sure, representing your binary states. And the idea is to perform operations in your qubits in order to get also qubits, right? But qubits in a different state, right? You're going to have an initial state of the qubit. You're going to apply a quantum operation. That quantum operation is going to be the quantum gate. After the quantum gate, you're going to have a different state of your qubits. So, for example, here, I have taken, this is the not gate, that we have just seen in the classical case. So this is the corresponding quantum NOT gate, and it's given by the sigma x Pauli matrix. Remember the Pauli matrix that we have discussed at some point in this course. So normally in quantum computing, I mean, remember that you can have people have normally a lot of names for the same thing. So in quantum computing, normally it's more common to call this operation just X, right? Just X. This operator is usually called X instead of Pauli X matrix. Out of, I don't know. I mean, it doesn't really matter that much. You just, I think people will understand if you say Pauli X matrix, but normally they say X operator, and that's good enough. So if you apply this operator, it just takes your qubit in state 0 and take it to state 1. And your qubit in state 1, and it takes it to state 0. So I mean, it's the same as this. The only thing is that this operation is quantum. I mean, if you have a linear combination of 0 and 1, it will also act in this way. In the sense that if you have, for example, alpha 0, beta 1, it will give you alpha 1 plus beta 0, right? I mean, because it just changed uh, your state, right? From 0 to 1 and from 1 to 0. And remember, every time we are writing a matrix, it is written in a certain basis. So this matrix is written in the 0, 0, 1 basis, right? Of our qubit silver space in this basis. Always, I mean, people normally don't uh, insist that much in this, but I think it's quite important in order to not get confused. So, yeah, that's basically it. So now there is a kind of, let's say, a problem, because um, if we see the AND gate and the OR gate, you will be probably thinking on how to convert that into a quantum gate, but that's not possible. in the sense that uh, using just, let's say, a quantum gate in order to in order to implement these classical gates, you cannot really do that using just a quantum gate. I mean, it is possible to to, to do this operation using more than one quantum gate, but you cannot do that using just one quantum gate. And why? Why is that? If you see here, it's I believe more or less easy to see that these are irreversible gates, right? Since and what's the meaning of irreversible? Irreversible is just that if you see the output, you cannot know the input. And for example, because if you have an AND gate and the output is one, you know that the input was one and one, right? But if you have output zero, right? What is the input? You don't really know what the input would be. Since you have three different options that give you the same output, right? If you have zero, it could be either be this option, this other option, or this other option, right? So that's why it is uh, irreversible because you cannot know the input knowing the output. That's the idea. And the same happens with the OR gate. If you have here the same output for three different inputs. So you cannot really know the input if you know that the output is one, for example. So and why is this a problem? So remember that in quantum we have just discussed in quantum system the evolution is given by a unitary operator. And if you see this relationship, uh, this is just saying that the self-adjoint operator is the inverse operator of your original operator, right? In the sense that for any matrix, I don't have a space for writing. That was here for any matrix. You have, I mean, the inverse operator is just the operator that gives you the identity, right? In the is this is the same as when you have maybe a number, let's say a, and just a number, and you multiply by a to the minus one. This will be one, right? I believe that the screen is frozen. So, uh, but let's call it fix as a moment point. Mm, so that's basically, yeah, now it's not frozen, right? So it's the same as just saying you have a number and you have the inverse of that number, it gives you one, right? This is a one. So the inverse operator is the same idea. I mean, if you are familiar with working with matrices, just the same. So if you have this relationship, we are just saying that the inverse of our operator, our time evolution operator, is just the the join operator. So this means that if our time evolution has an inverse operator or inverse matrix, this means that we can calculate the inverse of. I mean, if you have the final state, you can apply the inverse operator, and that will be the adjoint operator, and you get your initial state out of your final state. So the idea under this is that if you have a unitary quantum evolution, or unitary time evolution, that means that the time evolution is going to be reversible, right? That's that's the meaning. So if we have if the quantum evolution is reversible, that means that there is no way that you can uh, write these matrices as a quantum gate. I mean that you cannot write them just as a single quantum gate, but it is possible to do this operation using more than one gate. And, yeah, that would be a quantum circuit for sure, but we will see this in the next slides. And for example, I have here a very common, very useful quantum gate that is called the Hadamard gate, and is represented in this matrix. So basically, this gate what is that's this change of vectors. And remember, this plus and minus here are somehow related to the when we were seeing the thing, the up, the down. Or this will be the up. So the up and down states of your system that we were discussing, and we did the diagonalization. Remember that when we were talking about matrix diagonalization? So this just this vector, but in quantum computing, they normally call them plus and minus, and that's enough. But anyway, remember that the way you write things, it depends for sure on how you want to write them. So just always make sure that it's very clear what you are referring to, right? So this operation just sends your zero state to the plus state and your one state to the minus state. So that's the Hadamard gate. So an important idea here is that some classical gates, as for example the AND gate or the OR gate, they don't have a corresponding quantum gate, right? There is no quantum gate that can do that the calculation that these classical gates do, since this reversible and irreversible problem. But there are also some quantum gates that, that they don't have a classical equivalent, right? Because, for example, the Hadamard gate is give you a pure a zero or one state, and it gives you a quantum superposition of zero and one. I mean, there's no way you are doing that in classical gates, since there is no such a thing as quantum superposition in classical gates, right? I mean, it's impossible to have this on classical computation, because in classical computation, remember that you can just have either zero or one, so you don't have linear combinations of stuff or quantum superposition. So yeah, that would be an important idea. I mean, yeah, there are classical gates without a quantum corresponding counterpart, but there are also quantum gates without a corresponding classical gate. Mhm. A more probably difficult example of quantum gate. I mean, at the end, gates acting on a qubit, on just one single qubit, are going to be represented by a 2 times 2 matrix, a square matrix, right? As the Hadamard gate, or the quantum knot gate, or these single qubit rotations. These are quite important gates because they somehow rotate. Because remember the Bloch sphere we were discussing the other day. So if you look at that representation, when you perform this operation, this type of operation, at the end you are moving the angles of the Bloch sphere that we were discussing a little the other day. So that's why they are called single qubit rotation, because if you look at the Bloch sphere, they are at the end you are rotating the point in the sphere by certain angles depending on the rotation uh, you are performing, right? So this is basically the equation that gives you all these matrices in the general way. I mean, this is for doing a rotation of this angle using the direction given by this unitary vector. Right? For example, you have here the z direction. That will be the z axis. It will be the the j direction, and this the x direction corresponding to the corresponding axis in the 3D space. So understanding why this is like this requires group theory. Group theory. So that's why I have this in a orange orange square, right? And apart from this, in order to do this step here, uh, is basically the same as what we did in the first day in complex number when I prove that E equals this is equal to cosine of the d theta. Sorry, yeah, sine of theta. Yeah. When I proved it the very first day of this introductory course, which is Taylor's series, in order to prove this. So in this step, we are doing the same, exactly the same, but using here you have Pauli matrices, right? These are the Pauli matrices. So these are operators, but the idea is the same. So in case you want to try this at home and have any problem, just we can discuss it later. Right. So yeah, and these are just single qubit rotation along different axes. So that's some examples. Right. So quantum circuits. I mean, a quantum circuit is just a certain number of quantum gates that are acting on a qubit or more than one qubit. And for example, this will be just a one qubit circuit, and each qubit is represented by a line. So the line, for example, here we have two qubits. Each line represents a qubit, and this the evolution, the time evolution, is given in this direction, right? I mean, this will be the initial state here at the beginning. This will be the initial state, and following this direction is the time evolution. So this circuit just says that we have an initial state, in this case, a general linear combination of our qubits. Then the time evolution is going to be given by the X operator. That remember is the sigma X Pauli matrix. So the final state is going to be given by this guy here, this vector here that is just changing the 1 and 0 as we have seen before. For example, here also we have two operators acting, two different operators. So at this point, you have this vector. After going through the X operator, it changed to 1. And after going to the mm, to this Hadamard gate, is changed to this other vector. I mean, and in this case, you have one gate, so the 0 state changed to the plus state. So these are just quantum circuits. You can have more qubits, you can have more gates, and I will discuss a different type of gate in the next slides. But the idea is basically you have your qubits represented as a line, and you add gates on those qubits, given by the direction of the evolution that is given in this direction, right? Following that arrow. So, well, uh, so you can for sure there are very complicated quantum circuits for sure. Things get complicated over time. So, for example, here, and these are I'm not going to explain this on detail. I mean, and I'm not expecting you to see this and understand what is going on here. But this is, for example, the circuit for performing the quantum Fourier transform. And as you can see, this is an n qubit circuit, and you have 1, 2, 3 qubits until you get to the n qubit, and you perform different operations. This is a Hadamard operation. These are some type of rotation, and there is thing that I have not yet explained, but this kind of operation that they have a dot here, right? They have a dot. These are control gates. That's what I'm going to describe in the next slide. So, but this is just, for example, how the quantum Fourier transform circuit could look like. Also, for example, you have here another example of, for example, for the Gruber's algorithm. For example, here a gate acting on 2 qubits and gives you also 2 qubits output. Yeah, stuff like this. These are how we represent quantum circuits. Right. So control gates. This is the gate I told you I will describe. So control gates are just one more type of gate, but they have a special property, let's say, or basically they act on at least two qubits, and normally the more common control gate is normally on two qubits. So you have one qubit is going to be the control qubit, as you can see here, um, and the other qubit is going to be the target qubit. So the idea is that, I mean, uh, mm, don't think that that much in this symbol. I will explain this symbol later. But the idea is that depending on the state of this qubit, right? Depending on if this qubit is, I mean, right, with the x and j here, I just mean that x can be either 0 or 1, and j can be either 0 or 1 also, right? So that's, I mean, it's because in order to do it in for general case, instead of writing every single case for 0 and 1, I just write x and j, and they can either be 0 or 1. So that's a general case, right? Very well. So depending on this vector, whether it's 0 or 1, it's going to be doing a different operation here, right? That's the idea. Depending on the state of the control qubit, and that's why it is called control qubit, if we have some of effect on the target qubit. It can be either doing nothing or doing some linear operation, right? That's a control gate. So for example, take an example. This is the called the CNOT gate, and in here, basically, I mean, normally the CNOT gate is represented in this way, but this will be using this notation here. This will be equal to having your control qubit and the X gate. Remember that the X operator was the corresponding operator for the NOT gate, right? So the not gate is just a control NOT gate, right? A control NOT gate. So this operator is just the NOT operator that corresponds to the X linear operator, right? So, but normally, instead of writing this, in this case, they usually write this in this way, right? This is the X operator. So this gate basically is the if the control qubit is in the state 0, it does nothing, right? I mean, if the control qubit is in the 0 state, the control gate doesn't have any effect on the target qubit, and it leaves the same, right? Because when I mean, this is just how it works, and the idea is that if we have 0 state, you don't do anything to the target qubit, but if your control qubit is on the state 1, it is going to perform the NOT operation, right? And you can see here, we have this initial state, and now we have the corresponding final state that you have applied the X operator, right? Uh, Very well. So that's basically it. Yeah. An important result for quantum computing is that if you take the CNOT gate and also all single qubit protections, you can prove, and this is complicated to prove, but that you can make any single quantum circuit out of these gates, right? I mean, taking account that quantum circuit are going to give you a unitary evolution, because it cannot be other way around since the unitary nature of quantum systems in the time evolution. But every unitary circuit that you can imagine of, it can be made out of CNOT gates and also single qubit rotations, right? So that's important. So, uh, all right. So let's move to the final part. So it will be a little more complicated, but I hope to explain it easily enough. So we're going to be discussing this just an algorithm. So before going to the algorithm, I'm going to explain the problem we're going to solve, because this algorithm is its purpose is to solve a certain problem. So the problem is the following one. Imagine we have a function, a binary function, that it gets either 0 or 1. That's the input. That the input I will call x the input. So it can get either 0 or 1, and it can give you either 0 or 1 also. But you can have in this example, because we are just having here one bit or qubit in the input, we only have these four cases. If you have one, it can give you one and zero. It can give you 1 1 0 0 0 1 or, I mean 1 0 or 0 1, right? These are the four cases that we can find in this example. I mean, and you can do more complicated stuff if you, instead of giving just one bit, you could give a 13 combination, where you could be 1 1 1 0 0 1 and 0 0. In this case, there will be more cases for these functions if you have more inputs, right? And that will be more complicated, and you can do this with 3 4 bits, and in general you can do this with n bits. But in this easy example, we are just working with 1 bit or qubits, right? So we have two types of functions here. We have a constant function, in the sense that the input, I mean, it doesn't matter what input you get, that the output is going to be the same, right? So these are the constant function, and also the balance function, and that means that you get 0 and 1 equally. You see, there is 1 0 and 1 1, right? So you have 1 and 0 or 0 and 1. So we have these two types of function. So the problem is to if we have a function and we don't know which type of function it is, I mean, if whether it is constant or balanced, we want to know, or we want to find a way of knowing if the function is constant, or if the function is balanced. So this is the problem we want to solve, right? So in this case, since this is quite a easy case, and I mean that we are just using 1 bit here in the input, we will just need to we just need to call the function 2 times in order to know whether it is whether it's constant or balanced, no, right? Because if, for example, you have a function and I say, okay, give me this value, I give you 1, for example. All right, and now give me this value, 0. All right, so now I know that it's balanced, right? And that's a really stupid example, but you have classically you have called the function 2 times in order to know whether it's balanced or constant, right? But we are going to see that using quantum circuits, in the quantum case, we are only going to need one evaluation, and this will hold. This will be still be one evaluation if we increase the number of bits, because you can set, if you want, that if you increase here the number of bits, you say, as I said before, maybe you can have 1 1 1 1 0 1, and all possible combinations of this. You get a lot of more possible outcomes. So you need to increase the calls that you do to your function. In the classical case, they are going to be way more than just 2 calls. But in the quantum case, it is going to still be just 1 call to your quantum circuit. So that's quite interesting. And we are going to be explaining that in detail in the next slide. But just taking account that we are going to be using this control operator that we have seen before. And in this case, this function is going to be this f here is going to be our function, right? With our function, I mean that this f of x is going to be 0 or 1, depending on x, where x is also 0 and 1, right? And what's the meaning of this symbol? This is just some kind of certain special type of adding numbers, because since we are just working in binary logic, right, we have zeros and one. So if you sum a 0 with a 0, it gives you 0. If you sum a 0 with 1, it gives you 1 for sure. But if you sum one and one, it's going to be give you zero again because you can only have zero and one, right? So one plus one, for sure. Normally we will think that's two, right? That's two. But since two is not in our working place, right? We are just working with zeros and one. We are going to say that two is zero. So four would be one again, and that's the logic. So this is called module two arithmetic, and this two can be three, four, five, but in binary stuff is module two arithmetic. So that's only the meaning of that symbol. All right, so this is going to be the quantum circuit that we are going to need to solve this problem. So let's just start. So we have the in the beginning we have this state, right? Remember that we were when we were working with uh, more than one qubit, we were using the tensor product in order to do that. So normally it's more easy to write this in this way, right? So this will just be this initial state, right? Let's say I don't know one. Here we have this. So now let's take I don't know two. So now at that and in that step we have applied the x operator on the second qubit. So let's why x acting on 0 0, and since it is acting on the second qubit, we have 0 1, right? And if you want, this is equal to 0 1 0, right? Very well. All right. Now at this point, the the three, right? So we have applied a Hadamard gate on both qubits, and remember that the Hadamard gate takes 0 to the plus state and take the one state to the minus state. So this would just be H1, H2, 2, 0, 1, and this would be plus minus, right? I mean, you can also write this using the tensorial stuff, but normally you don't do that. I'm just doing that in order for you to maybe understand this better. Yeah, to have a better understanding of this, but I hope it's clear enough. At this point, we face with something a little more complicated, but we are going to do something because this final step here at the end plus minus this is the same as sorry, uh, 0 plus 1. This is the times this. I mean this is just the plus 1, right? If you want to add here the 1 here, I mean there is no need to put the numbers in order to specify the number of your qubit, but I'm doing that just out of in order to be more clear, right? Anyway, so now how do we perform this operation? So let's take a general case. I mean, because we are facing with this, right? So I'm going to see for this case, right, when I have x and minus here and u the f. So x now can be either 0 or 1. I mean, since I have here 0 and 1, I'm just going to be doing that case for both of them for both 0 and 1 at the same time. So if you remember this acting, well I'm going to write there. This is the minus state, 0 and minus 1. So this is going to be acting in this way with the thing x, right? Since all right, x is the first qubit, right? Is the first qubit, so it's the control qubit, right? In my in this abstraction that I'm doing, x is my first qubit and it is the control qubit. So it doesn't nothing happens to the control qubit. I haven't said that before, but nothing happens to the control qubit. So the control qubit stays the same, but these other guys suffer this sum. Well, let's take this down here. That's plus, no, minus, sorry. Right. So we have this, right? So now just take, because we have f of x and f of x here. So we know that f of x can be either 0 or 1, right? So let's take the case. Let's take the two cases. If f of x, and we don't know what is x, but we know that f of x, whether x is 0 and 1, x will be, this function will be 0 or 1, right? So imagine this is 0 for the first case. You will have x times, I mean, and this is this sum for sure. Sorry about that. If it's 0, it will be 0, and if it's 0, this would be 1, right? So in this case, you have the very same. I mean, x all times minus, right? Because this is the minus, it have done nothing. But if you have the, if this is 1, if we have, you will get, in this case will be 0 all times 1, and this is just 1, and you will have here 1 all times o plus, sorry, I'm saying all time, but it's o plus, o plus 1, and this will be 0. So this is just minus this other vector here. Yeah. So take the minus out, so there will be a plus here and a minus here, and it will be the same, right? So basically, what we have proof in this little calculation. I mean, the time is running out. I mean, we are reaching the end, almost. So what we have proof is that we have this operator active. Okay. We get minus 1 to the power of f of x. X minus. This is what we have proof here. Since when this is 0, you get the same, right? If this is 0, you get, this will be 1, right? But if f of x is 1, it will be, you will get a minus 1 in your state. So that's basically it. So going again to this state here. This, well, and now let's take, sorry. So if we go to this point here, let's call this 4. So in 4, we have this operator acting, this control operator, and using this result, we see that we get in here is f of 0, right? Applying onto this operator, and we get 0, since it's the same x, plus minus to the power of f of 1 times your 1 state, all times, no, it's all time, oh my god, all time, this, okay. Right, we have just used this. Uh, Very well. So, so at this point, what we do? Now we apply a Hadamard operator on the first qubit. Right? So let's say 5 here, right here. And changing the colors, I don't know why, but hope it is not confusing. I mean, I know there is no special reason for changing the colors. Um, yeah, so this is our final state. I'm going to call, yeah, this is going to be H acting on the first qubit to the state, to this state, right? Because this state is just this state here. So I'm just going to change, yeah, the, the moment. Yeah, right. Well, yeah. Before doing that, let's go. I mean, it's not really necessary to do this step, but let's say if f is, let's say study the two cases where we want to prove. Let's say f is constant. If this is true, this means that these are the same, right? It doesn't matter. So you will get at the end, you this this state that we have here is going to be just plus minus the plus state and the minus state. Yeah, 1 and 2 here is 0. And if it is balanced, and this means these guys are different. Yeah, you get that this is, and the plus minus is just for because these are equal, but they can be either 0 equals 0 or 1 equals 1, right? It depends. As these are not equal, but they can be 0. It could be 0 or 1, or they can be 1 or 0, right? So that's why there is a plus minus depending on the type of constant or balance function that you have. But this would be plus minus. This would be a minus. So I understand that may be a little more difficult to see, but just the only thing you have to do is put here the numbers. I mean, I'm not doing that because we are running a little late on time. But the only thing you have to do is put this expression here and do the calculation using that case, and you will see that you get this state here, right? And also the same with this, you use that, for example, use here 1 and 0 for this case, or 0 and 1 of the, and you will get either plus or minus this state. So if you do that calculation, it's not difficult, just try and put here the values. You will find that depending of whether the function is constant or balanced, you will find you have this state or this other state. So now, knowing that, and if we apply the Hadamard operation, mm, we have this result, right? I mean, we will have plus minus 1, no, 6, sorry, 0 times minus 2, or plus minus 1 times minus 2 if if the function is constant, if the function is balanced, right? Yeah. So basically, we have solved our problem because we see that we can know what type of function we are working with using just one quantum circuit. Because if we do this quantum circuit, we will get either 0 if the function is constant, or we will get 1 here in the first qubit if the function is balanced, right? So that's what I do in the last step here. And this operator here is not really an operator, it's just a symbol for indicating measure. Measure. So in here you just measure the first qubit. So, and if the function is constant, you will get 0. and if the function is oh, this, here you have a I forgot to if the function is constant you get 0, and if the function is balanced you get 1, right? So this will be cross here, not equal, right? Yeah. So we have now work with a quantum circuit that solve our problem using just one code to the circuit, because we just need to apply the circuit and measure. If you measure 0, you know your that your function is constant, and if you get 1, you know that your function is balanced. And this always works more or less the same, even if you have more qubits, and that means you have in your problem you have maybe more combination of things. And for the classical case, you will need more calls, and you will need to be proving with more calls in order to know if the function is constant or balanced. But in the quantum case, you will always need just one call to this operator. I mean, if you have more bits, you will need to add here more qubits, right? But the circuit idea is more or less the same. So I hope that's more or less clear. I mean, I understand that the calculation can be a little difficult at some point if we are not used to do this kind of calculation, but these are the calculations that you normally work in quantum circuits. Also, when you do more complicated stuff, that is for sure more difficult than this. But this will be a beginning, right? So that will be everything for today. Here are some references. These references are the same for the other lecture for the qubits, since all that we are discussing is in the always in introductory quantum computing books and stuff like that. So you can search all in the same books in order to see things about quantum circuits. Yeah, that will be everything. So if there are any questions or whatever, as always, feel free to write on the chat or anything. Well, see everyone. The next final day of this introductory course, we will be dealing with implementing qubits using trap ions. So see you on Friday.